that time can be wired to the spatial dimensions in a non-trivial way, so that the time-space dimensions have curvature, where we know now pretty clearly what we mean by curvature of time-space. Okay? We know that the space-time connection is simply the derivative of the metric coefficient, or actually the derivative divided by itself, whatever. When we had gravity, we said that there's a function over here that's the potential, a function of r. We took that function, we took the derivative of it with respect, not to t, but with respect to the other dimension coordinate, r. So we had phi prime, phi with respect to r. That gave us the relationship between the two dimensions, the space and time dimension. That was the connection. The connection relates the two dimensions, time and space. How does it do it? It takes the metric coefficient in the time thing and takes a derivative with respect to the other dimension, namely the space. So we had phi prime. The other way of doing a time-space connection is taking the function in the spatial part of the metric and taking its derivative with respect to the other dimension, which is time. So here you have r of t with respect to t, as opposed to g of r with respect to, or phi of r with respect to r. So two different ways of taking a connection between time and space. One gives you gravity, the other gives you universal cosmic expansion. That was a space-time curvature. And you ended up having the space-time curvature connection. Because of this r in front of the spatial part, you took a derivative with respect to t. Okay? And that's the crucial point there. The connection, which told you how the space and time dimensions are connected to each other, takes this time function and takes its derivative with respect to the other coordinate, the other dimension, namely t. That's the connection between this dimensions of space and the dimension of time, in the same way that gravity did what? It also was a space-time connection. But there it took a function of r, namely the potential in the t part, and took its derivative with respect to the coordinate of the other side, namely the spatial side. All right? So you had a spatial function in the t part, derivative with respect to r. That was the connection of the time dimension and the space dimension here. The connection between the time and space dimension, which reflects itself in universal spatial expansion, is also a derivative. So if the metric coefficient is some function r of t, the connection will be r dot, or actually r dot over r, to be more exact. Okay? What would the Riemann tensor components, what will the Riemanns look like, the curvature things? Well, we know the Riemann curvatures are the gamma prime plus gamma times gamma plus gamma times gamma, things like that. So we won't be surprised to find that the Riemann tensor components, the curvature, will be things that have to do, this is the metric, this is the connection, it'll be this derivative. In other words, in this case, it's derivative with respect to time, so it'll be r double dot. And also products of these things. So it'll be r dot times r dot. In other words, r dot squared. So we won't be surprised to find in the Riemann tensor components things like r double dot, where this is r, and r dot squared, where this is r. The field equation, the Einstein field equation, will be a sum of a bunch of these guys, and that will be equal to the source term. Namely, what will the source term be? It'll be the average matter-energy density of the universe. So we're going to have an equation which is going to relate on the left-hand side something like this, equals, take the whole matter-energy of the universe, divide it kind of per volume, and get the average. And that's in fact what it turns out to be.